BAMO stands for Bay Area Mathematical Olympiad. It's a high-level math competition. This is a geometry problem of the competition in 2012. Let AB be a segment and M an arbitrary point on AB. Create two equilateral triangles AMD and BMD on the same side of the segment. The circumcircles of the triangles intersect at 2 points. One is M, the other is N. We have two questions. First, prove that AD and BC also intersect at the point N. Secondly, as M is moving, line MN passes a fixed point K. Let's look at the first question. N is on AD and BC. We know N is an intersection of the two circles. Let's look at the circles on the left side. We connect N with the three nodes of the triangle ACM. We know ACM is equilateral, so angle C has 60 degrees. By the inscribed angle theorem, the angle ANM is also 60 degrees, as they are both inscribed angles of the arc AM. Similarly, the angle ANC and the angle AMC are also 60 degrees, because they are inscribed angles corresponding to the minor arc of AC. As a result, when we connect N with AMC, we created two additional angles. They are both 60 degrees. Following exactly the same argument, on the circle of the right side, the angles M and B and the angle B and D are also 60 degrees. Let's put everything together. Both the angle AND and BNC are the sum of three angles of 60 degrees. Therefore, they are all straight angles. We are done with the first part. Part 2. When M is moving, line MN passes a fixed point K. Question: how do we find the point K? First, let M be the midpoint of AB. Then we have two congruent triangles, and the graph is symmetric to the line MN. So, MN is the perpendicular bisector of AB. We can also use a different point M and draw another line of AB. The intersection would be the point K. If we draw the graph accurate enough, we can have a good guess. Triangle KAB is an equilateral triangle. Yes, it is indeed the case, but how do we prove that? In most of the cases, two circles have one radical line. If the circles intersect, the radical line is simply determined by their intersections. Here is a very good property of the radical line. Any point P on the radical line has equal power to the two circles. We draw tangent lines from P to the circles. Let Q and R be the tangent point. From the left circle, PQ squared equals PM times PN based on the intersecting chord theorem or the power of a point theorem. From the left circle, from the right circle, PR squared equals PM times PN, therefore PQ equals PR. No matter where P is, PQ always equals PR. More importantly, its inverse is also true. If PQ equals PR, then P is on the radical line of the circles. In other words, P is on the line MN. This is a very useful tool to prove collinearity of 3 points. Now, let's go back to our target point K. Why is this point so special? It seems that Ka and Kb are tangent to the circles with A and B as the tangent point. If this is true, and we also know Ka equals Kb, then K is on the radical line, which is determined by M and N. Then we are done. So the only thing that remains is to prove that Ka and Kb are tangent to the circles, no matter where M is. Let's look at the animation again. Yes, it is indeed the case. Let's prove that. Let S and T be the centers of the circles. Then SA and TB are radius of the circles. We want to prove Ka and Kb are perpendicular to the radius. This can be easily done. We have so many equilateral triangles here. So as the angles SAK and TBK are all right angles. They are the sum of 30 degrees and 60 degrees. As a concluding remark, radical lines of 2 circles and the radical center of 3 circles are extremely useful in high-level math competitions. I'm going to produce another video to discuss this concept. Stay tuned.